Okay, so we have seen the relation between the coordinate volume informs. So why we call it coordinate volume? So there are reasons why you call it. To define actual volume, you need a notion of distance, right? Like you need to measure length to find the volume, to actual volume. But when you have set up a coordinate, in terms of coordinates only, you could say like you have a volume. Just that volume element is constructed out of the infinitesimal changes in the coordinate, and to do that you need not to have a metric tensor. So even without having a metric tensor, you can have a coordinate volume, but to find a real actual volume, you need a metric tensor.
Yeah.
So in Cartesian coordinate, a coordinate volume element would be like dx times dy. In polar coordinates, a volume element would be like dr times d phi, like that in 2 dimension. Just infinitesimal changes in the coordinates that are multiplied. So that doesn't mean that it is actually a volume. But to find actual volume, you need a notion of metric tensor. That means notion of distance. So we are going to define a really important quantity, that is determinant of a metric tensor. Determinant of a metric tensor, it could be positive or negative depending on the signature of the space, meaning like okay, signature of a space, it actually means when you add the diagonal component, it's like how many components, how many diagonalized components have negative sign versus how many have positive signs. So if you have like 2 negative signs and 3 positive signs, then your signature will be +1, like that. So that matters here. So how many parts? So determinant of a metric tensor in principle can be positive or negative. So it's not necessary that when diagonalized, component of a metric tensor are positive. It's not necessary. It could be negative as well. We see in special relativity. So we have like time direction as with a negative sign. So that can be happen. So okay, so the determinant of metric tensor, so date or metric tensor constructing a determinant out of metric tensor, usually written as just G. It could be a positive or negative quantity. That's what I want to emphasize. So what's the definition of G? Definition of G is take the component of metric tensor GS square. So those are G mu nu. Out of G mu nu, construct a matrix that is G1, G01, or let's write this way: G11, G12, G21, G22, like that, with lower index, remember, and then take a determinant of the whole thing. So that's how we define our G. Metric tensor with 2 lower indices. Take those components and construct a matrix. Then take the determinant of the matrix. That's your determinant of metric tensor. That's what you mean. So that is your G, small g. Is the definition clear to everyone?
Yeah.
So how do we write it mathematically in terms of E? How do we write it in terms of E? E means curly E that we have defined today. So E equals to E with lower indices like mu1, mu2 up to mu n, it times G, which is the determinant, equals to E with upper indices mu1, mu2 up to mu n, G mu1, mu1, G mu2, mu2 up to G mu n, right? So you could say this is our definition of G. Is this statement clear to everyone?
I'm not clear.
Okay, so for
We
any object, we had the definition of determinant, right? Probably in this page, like
yes.
this. Remember? We are just, instead of substituting T, we are substituting metric tensor itself.
Okay.
That will give you this thing, the final result.
Okay.
Okay, great. So we understand at least this thing. Now we are actually more interested about seeing the coordinate transformation, because we want to connect metric tensor with Jacobian. When metric is defined, Jacobian is connected to metric tensor. So that's what we want. Say you go to another coordinate system. So instead of you were using X coordinate system, now you go to X prime coordinate system. Previously, in X coordinate system, the component of metric tensor was G mu nu. Now, when you change the coordinate, the components of metric tensor is G mu prime nu prime. And we know G mu prime are related to the older coordinate. G mu prime are related to the older coordinate by the relation. Can you tell me what are those? It's a second rank tensor, so we should know the relation.
Del x
Delta x.
mu prime.
Is it mu prime or mu?
Mu.
Without any, yes. So then say
Delta
mu.
x mu prime times delta x mu delta x mu prime.
Yes. So then G mu mu. This is the relation, as it is a second rank tensor, right? We already saw this in a previous class. I can proceed with that. Okay, great. I can proceed with that. Then I can actually, by just inverting the relation, I could write like this: G mu nu equals to something times G mu prime. And what would this something be? What would that something be? I'm just trying to invert the relation.
Inverse relation.
Yes, what's that?
Delta x mu prime
Mu prime
divided by delta x mu. And delta x nu prime divided by delta x nu.
So is it clear to us that transformation rule can be inverted like this? We have seen it several times.
Yeah.
Okay. Now say you construct a matrix out of G mu prime nu, like both. Say first you construct a G, like the matrix of G mu mu, and taking determinant of that thing is defined as G, and it's just a name. And another name is, if you take determinant of G mu prime, because those are different numbers, so taking determinant of that thing will give you something new. Let's call it G prime. So G prime is the determinant of metric tensor in new coordinate. Okay.
Yes. Okay.
Okay, great. So now, using this relation, I want to substitute this G mu1 nu1, G mu2 nu2. Instead of those, I want to substitute primed coordinate. I want to substitute primed coordinate. So what should I do then? So in my left hand side, I still have E mu1 mu2 up to mu n times determinant of old coordinates metric tensor, right?
Yes.
Yeah.
I'm trying to connect it with the coordinate metric tensor with new coordinate. Okay, so then on the right hand side, I should have E nu1 nu2 up to nu n as I should have. But then instead of having G mu1 nu1, I want to write in terms of newer coordinate, like G prime I want to introduce over there. So what should I substitute then?
I can substitute the term G mu delta X mu
X
mu
mu.
prime.
We have multiple mu's, so let's call it mu1 prime.
Okay, mu1
We
prime.
do not just have one mu, we have multiple mu's.
Okay, yeah.
By delta, we also have multiple mu's as well. So let's call it mu1.
Okay.
Then delta X sorry, it's mu1, right? I wanted to write mu1, not mu1. And then delta X nu1 prime by delta X nu1. Then I can write G mu1 nu1, right? So this is the whole thing. I'm actually substituting instead of just this one term. I have to do this for every terms. Is that clear to everyone?
It would be mu1 prime, mu1 prime.
Huh?
Okay, you forget
G mu1 prime and nu1 prime.
mu1.
Oh, yes. So here I should put a prime thing, right? Okay. Is that correct now?
Yeah.
Yes.
Okay. Is it clear to everyone? I have just written one term. I have to write more, many more. So instead of just writing this just one term, I have rewritten this part. So now I have to rewritten the second one as well. So what it should be? Delta X mu2 prime by delta X mu2 delta X nu2 prime by delta X nu2 times G mu2 prime nu2 prime, right? And so on.
Yeah.
And so on. So dot. Let's write the nth term. What's that?
Delta X mu n prime
Delta X mu n prime
by delta X mu n.
Mu n delta X mu n prime by delta X
Nu n.
mu n times G mu
N prime.
mu n prime, right?
Yeah.
Okay. Now we already seen a relation. We have already seen the relation that n factorial times Jacobian matrix, determinant of Jacobian matrix is what?
Kronecker delta. Is that called Kronecker delta?
No, it wasn't Kronecker delta. It was something epsilon. What was that?
It was epsilon, sorry, E.
We derived it somewhere.
Yes.
Here, this one. So we need two E's, right? We needed two E's. So one set E is like nu1, nu2 up to nu n. Another is E mu1 prime, mu2 prime up to mu n prime. Then we have delta x mu1 prime by delta x nu1, delta x mu2 prime by delta x nu2 up to delta x mu n prime by delta x nu n. This is what we derived earlier. So as you can see, we have already this E over here. Do we have these things? Do we have those terms?
No.
Actually, we have here this term, that term, that term.
But they are not same.
Why they are not same?
Because
The
they are.
derivation.
Look. Here I have like unprimed indices. So primed indices are differentiated with respect to unprimed indices, and those unprimed indices are summed over with E. That's what's happening here.
Yeah, and they are
We are
dummy
missing
indices.
this term, obviously. We are missing this E. We are missing
Actually,
that.
mu1 prime and nu1 prime, these are dummy indices. So that's why they are same.
Yes. So only we care about they are primed or not.
Okay.
They are appropriately primed. Like we want the primed coordinate differentiated with respect to the unprimed. That's what we have already.
Yeah.
So what you do is first multiply both sides by E mu1 upper indices. So here we write this like right hand side. E mu1 mu2 up to mu n, E lower mu1 mu2 up to mu n times G, which is, so these are both summed. Then what it should be? If you sum over all of E, what do you get?
Factorial.
You get n factorial. Great. You get n factorial. This is right, left hand side, right? What happened to right hand side? Right hand side, you can actually collect this E nu1, nu2 up to nu n with, you have these terms, right? So delta nu 1 prime by delta nu 1, delta nu 2 prime by delta nu 2 up to delta x nu n prime by delta nu n. Then we have our the second terms, like second similar terms, that is delta x mu1 prime by delta x mu1, delta x mu2 prime by delta x mu2, like I'm writing these terms if you are not able to follow these terms.
Yeah.
Delta x mu n prime by delta x mu n. We can do that. And we have multiplied on the other side like epsilon upper mu mu indices. So we should write that as well. Actually, let's write it later. So then we have our G. We have our G. Let's write those down as well. So G mu1 prime, G mu2 prime up to G mu n prime. Isn't this correct? Then we multiply here.
You have missed a G, n factorial into G. That would be n factorial into G.
Where did I miss?
The middle term. Middle term. N factorial into G, I think.
Oh.
It is.
That's left hand side I missed actually.
Yeah.
Now it's correct, I believe.
Yeah.
So I have multiplied both sides by E upper mu1, mu2, mu n. And this is what I get. So this part, it's almost started to look like the expression of Jacobian determinant, right? This term, like let's make a box over there. So this term actually I'm talking about first. It has started to look like something multiplied by determinant of Jacobian. Also, this part has started to look like the same. This part. So let's calculate then, right? So E upper indices with this thing, what can I write in terms of J, where J is the determinant, Jacobian determinant?
Which one?
These things.
To get J, we have to multiply it by.
No. The original definition of determinant. Remember that. What was that? It was like E.
Okay. E mu1 prime, mu2.
Upper. Yes. E
Yes. mu1
prime, mu2 prime up to mu n prime.
Yes.
Times
Jacobian determinant
x
of
by x.
Yeah.
Yes.
This first green box, according to the definition of determinant itself, right? Then apply the same thing here as well. The second green box. What do you get?
E upper mu1 prime.
E upper mu1 prime,
mu2 prime,
mu2 prime up to mu n prime.
Yeah.
Times
And Jacobian determinant.
Jacobian determinant. And then you have your G left, right? G mu1 prime, mu2 mu1 prime, mu1 prime, G mu2 prime, mu2 prime, up to G mu n prime, mu n prime. So now you have your Jacobian determinant squared, right?
Yeah.
Jacobian determinant is squared, and what else?
E mu1 prime, mu2 prime, and the mu1 prime, mu2 prime.
Yes. E nu1 prime, nu2 prime up to nu n prime, E mu1 prime, mu2 prime up to mu n prime times G mu1 prime, nu1 prime, G mu2 prime, nu2 prime up to G mu n prime, nu n prime, right? So this part, for this part I can apply the definition of determinant itself again, right?
Yeah, it's G prime.
Yes. So what do you get if you apply that?
G prime.
So you have like E nu1 nu1 prime, nu2 prime, right? Up to nu n
Yeah.
prime. That's you have.
Then G prime.
Then okay, G prime. What else?
And it's E upper nu1 prime.
It's not upper, it's lower.
No, it's lower. Yeah.
E nu1 nu2 nu1 prime, nu2 prime up to nu n prime times G prime.
Yeah.
So now on the right hand side you already have G times n factorial, and again you have this sum over E. So what do you get over there?
N factorial.
So n factorial times
G
G
prime.
prime. So finally we have our relation between the metric tensor of transformed coordinate and old coordinate with the Jacobian, like determinant of metric and Jacobian. Those are related by this relation. G by G prime equals to J of this, right?
Yeah.
Okay. So now what I can write. So if you want to take a square root over there, then what do you get? Obviously, you should write square root of G. I am putting this absolute value sign. This is not a determinant sign. This is absolute value sign because you are taking the positive part only. Actually, this step you need not to do that. This step, let's write it like this. I'll explain why. Then if you want to split this square root, if you want to take the square root individually, then you have to be careful, because they could have a minus sign. So you cannot take minus square root of something minus. So what you do, you take the absolute value like this.
Yeah.
We are still finding out the relation of Jacobian determinant, not just the Jacobian.
No, yes.
Yes.
You want to write like this. So Jacobian matrix is never used here. Like never used means like we are not finding the relation between Jacobian matrix itself. The Jacobian determinant is the thing that we are looking for. So we have proved a beautiful relation, that is square root of absolute value of G is basically transforms as Jacobian of x prime by x times square root of G in new coordinate, right? Here actually I should put prime over there and then, yeah, like that. So this is a really important relation here. Now we are ready to actually explore the power of this thing. Previously, we found the relation between the volume elements, remember? Infinitesimal volume elements.
Yes.
What were that? Like coordinate volume relation elements. What was that? Dx
1 prime
1 prime
with
wedge
dx2 prime
dx 2 prime wedge up to
dxn prime
n prime equals to
Jacobian determinant
j this thing
into
into
the wedge products in unprimed
dx1
coordinate.
wedge dx2 wedge up to dxn, right? I can now replace this Jacobian in light of our metric tensor itself, right?
Yeah, we can.
So now I can write my Jacobian as like
Root over G, absolute value of G divided by absolute value of G prime.
okay, okay, yes. So this, right?
Yeah.
Now I can multiply both sides by square root of G prime. Absolute value of square root of G prime, right? That will give me
Yeah.
so now if you are in an old coordinate, here the instruction says you are just taking the metric tensor, like determinant of metric tensor, and taking square root of it, and you are multiplying by the coordinate volume element. And when you go to the new coordinate, instead of manually transforming the coordinate, you could actually take the metric tensor of new coordinate, like determinant of square root of determinant of metric tensor in new coordinate, and just coordinate volume in new coordinate, and that would be like the true transformation relation, right?
Yeah.
So we can define this thing as our volume element. We call this as actual volume element. It's not coordinate volume, it's real volume, or this thing, volume element. Volume element in n dimension. So you see, to find true volume element, or basically this gives you the true volume, you actually need the notion of distance. The metric tensor is required. To find coordinate volume, like to find coordinate volume element, you need not to have your metric tensor defined, but here you need, because it's the actual volume. And it has a specific name. It's a tensor, obviously. By construction, it's a tensor. So it's written as this. It's the epsilon tensor, or Levi-Civita tensor. Levi-Civita tensor is the infinitesimal volume element in n dimension. Why we write epsilon? There is reason. We'll see that. Okay, do you have any questions so far? Actually, I'm almost done. Actually, I've done the hardest part. Do you have any questions so far?
Does
No.
that volume element has the dimension of volume?
Yes, yes. It has the dimension of volume. Like
How
length
can we?
or n.
Dimension of volume or length, area, it depends on the dimension.
Yeah, like if you are in n dimension, it has length to the power n.
Yes.
Yeah.
If you are in 3 dimension, then it's like length cube.
Cube.
We'll see more examples actually. I'm just constructing the theory first, then I'm going into the examples. Okay, so what are the components of epsilon then? Say your epsilon equals to in a particular coordinate is this. What are the components of your epsilon? I want to write as 1 over n factorial component of epsilon. Let's write E epsilon mu1 mu2 up to mu n. Then here I want to write dx mu1 mu2 dx mu2 wedge dx mu2 wedge up to wedge dx mu n. I want to write like that. Then what are this epsilon are?
It's the E. I mean the permutation symbol.
Just
Lower.
E. So you're saying that E epsilon mu1 mu2 up to mu n is E with lower indices like mu1 mu2 up to mu n. Is that correct, or you're still missing something?
I'm not.
There is another entry, I think.
Okay. Yeah. Oh, okay.
See, like this part actually, this part could be written like that. You could write like, except for that square root of g, the rest part can be written 1 over n factorial E mu1 mu2 up to mu n dx1 wedge dx2 wedge dot dot dot.
So the component will be E multiplied by the root over of metric tensor determinant.
Yes, so you should have like this thing as well.
Yeah.
So these objects are now tensors. Like in epsilon mu1 mu2 up to mu n, these are the component of tensor. Whenever you go to the new coordinate system, you have your E multiplied by this square root of g. So even if you go in new coordinate, it remains same. The form remains same.
And that root over g term responds to the transformation. Yeah.
Okay, so these are our well-behaved tensor. So I'm almost done actually. I just need one more algebra. So things with E upper indices, that's what we need. E epsilon upper indices. So we know that epsilon with lower indices are like this, square root of this thing, and that's all. So how this thing, epsilon with upper indices, say mu1, mu2 up to mu n, are related to something times E with upper indices, mu1, mu2 up to mu n. This is the final thing we need to know here. Any guess? How do I get it?
We had a uppering and lowering indices relation.
Yes, we have an uppering and lowering indices relation for tensors, right?
Yeah.
For epsilon as a tensor, we can actually upper and lower systematically. So obviously, this uppering of epsilon, as it is a tensor, component of a tensor, we can actually apply this thing. G with say mu1 G mu2 up to G mu n times epsilon with lower indices mu1, mu2 up to mu n, right?
Yeah.
Okay. Now we can actually substitute epsilon for E for epsilon. So that will give you G mu1, G mu2 up to G mu n, then E mu1, mu2 up to mu n times square root of norm of G, right?
Yeah.
Now, if you take this thing, consider just this part. Do you see something that could be useful?
We can, I guess we can just use express it in terms of determinant of that tensor.
Okay. Yeah, determinant of what? So epsilon, epsilon, sorry, not epsilon, E mu1, sorry, not mu1, mu2 actually, right? mu1, mu2 up to mu n, then determinant of
G.
Determinant of G. Which object are you taking determinant of? Remember, these are G
That's
upper
inverse.
Yes, it is the determinant of inverse matrix, right?
Yeah.
G, let's call it bar, or just call it G bar. Determinant of inverse matrix.
Yeah.
Times the square root of this thing. So we got that epsilon with upper indices is actually similar, but you have to take determinant of inverse metric tensor times determinant of original metric, the square root of absolute value of original metric tensor times E. Question is how G bar and G are related. How G bar and G are related. That's the question.
Reciprocal.
How can you tell that?
I think there is a property of determinant that determinant of inverse matrix is 1 by the determinant of matrix.
Yes, exactly. So we can actually do that formally. So we know that G mu nu as nu lambda, say, equals to Kronecker delta
mu lambda.
So now take determinant on both sides. So construct matrix out of it, out of this relation. So this is nothing but matrix of G bar times matrix of metric tensor or ds square, like that, equals to identity, right?
Yes.
Identity matrix. So if you take determinant on both sides, we get this, right? So determinant of identity is what?
1.
Determinant of identity is always 1. And so you get determinant of G bar, matrix of G bar times determinant of matrix of ds square equals to 1. And by definition, determinant of G bar is just G bar. Actually, no, let's not write G bar, because G bar we are considering as tensor, we are denoting like that. So how do you denote it? Let's call it G star. Let's call it G star. So it's G star times det of ds square, which is just G equals to 1, right?
Yeah.
So G star, we actually not going to use it G star anymore, which is 1 over G. So I can substitute that over there. So it is square root of absolute value of G divided by G times E mu1, mu2 up to mu n. Okay, I think I'm officially done with this algebra portion. I can actually summarize now. Any question?
Are we still on chapter 4 of the book?
Actually, I'm teaching some portion of chapter 3.
What did you say?
Chapter 3. Chapter
Okay.
387. As I said, I'm not following exactly as the book. So
Thank you.
I'm going to summarize it again. Also, next day I'll start the class with summarizing the whole thing because it's a long thing of algebras. So many people might get lost by this time.
It's like doing a lot of messy algebra in exterior algebra, but finally we get nice relations.
Yeah, finally, when we get nice relations, then everything will come into one place. That's fall into the place. That's the best part. So let's summarize. Let's summarize the theory of P form. So far we have learned. So a P form, if it's a P form is a alpha, then it can be written as 1 over n factorial alpha mu1 mu2 up to mu n in multiplied by dx mu1 wedge dx mu2 wedge up to dx mu n, right?
Yeah.
Okay, then what did we learn? We learned the definition of wedge product itself, right?
I mean,
So
defining properties, 3 properties.
defining properties, yes, defining properties. So what are those defining properties? So this is a P form, wedge product. Actually, let's write P vector as well, right? Okay, a P vector can be written as, let's call it P vector W. It can be written as 1 over n factorial W mu1 mu2 up to mu n, then E mu1
Yes.
E mu2 wedge up to E mu n. Okay, then wedge product we have learned. So what are the properties that wedge product satisfy?
One is
A alpha,
alpha,
B beta is the linearity property, right? Which some gamma, another one form, actually P form, some P form. Now what's the value of P? You do not know. So A, yes.
Alpha wedge gamma.
Yes, A times alpha wedge gamma
Plus B
times
B
beta wedge gamma. What else? Alpha
associativity.
wedge beta wedge, yes, associativity. Alpha wedge beta wedge gamma. So you can do any part earlier, any part later, doesn't matter. Which is basically alpha wedge beta wedge gamma. So unlike cross product, we do not have that confusion like which part you have to do first. Then we have like the commutation relation, commutativity. That is, if alpha is a P form, let's say it's a P form, and beta is a Q form, then if you switch that, you get a -1 whole to the power P times Q beta wedge alpha, right? This is how we use wedge product. The same thing is true for vectors as well, like for P vectors as well. But you cannot take wedge product between a P form and P vector. That's, you have to be careful. Then we have learned a P form, like a basis P form. Basis P form. It can be written as like it's not P form. It's actually, we're talking about N form here. A basis N form can be written as basis N form is like dx1 wedge dx2 wedge up to dxn, right?
Yeah.
Or you could say coordinate volume element, as you can say it as well. So coordinate volume element. Coordinate volume element. Both names are correct. Okay, so we were able to write as 1 over n factorial. Then in terms of E, how? E mu1 mu2 up to mu n dx mu1 wedge dx mu2 up to dx mu n, right?
Yes.
Okay, permutation symbol. So how E were defined? E mu1 mu2 up to mu n are just same as E upper mu1 mu2 up to mu n equals to either +1, -1, or 0. For even combination or even permutation, you have +1. For odd, you have -1 and 0 otherwise, right?
Yeah.
Okay. Then we had another permutation symbol, basically Kronecker delta. It's Kronecker delta. So it's defined as, it could be like up to P indices. So mu1, mu2 up to mu P, but dimension could be n. Mu1, mu2 up to mu P is defined as +1 one set is even in another, right?
Yeah.
One set of indices are even in terms of the second set of indices, right? One set is even in another. -1 if one set is odd in another, and 0 otherwise. Okay, so these permutation symbols are connected. For like for E with n indices, it's connected. So how? E say mu1 mu2 up to mu n, E mu1 mu2 up to mu n equals to delta mu1 mu2 up to mu n, nu1, nu2 up to nu n, right?
Yeah.
Okay. Then we learned definition of determinant, right?
Yeah.
So how did we define it? It's E with upper indices like mu1, mu2 up to mu n equals to E, not equals to, times matrix of T, which has two upper indices like this, equals to E. Now we need lower indices, nu1, nu2 up to nu n, T mu1, nu1, T mu2, nu2 up to T mu n, right?
Yes.
Yeah.
So for lower indices and so on, you can actually construct it by yourself. It's just a matter of notation, right? Okay, then what did we learn? We learned few relations, remember?
Yeah.
So change of volume. So new coordinate, like volume element in new coordinate dx1 prime wedge dx2 prime wedge up to dxn prime is related to the old coordinates like this, where this j inside of this bar is basically determinant of Jacobian matrix times dx1 wedge dx2 wedge in terms of old coordinates, right? Like that.
Yeah.
Okay, so then we defined, then we had a relation between metric tensor, right? So the relation was square root of g divided by square root of g prime equals to j, right? Using this, we were able to define our actual volume element. So we call it volume, just volume element. Volume element. It's written as epsilon Levi-Civita tensor E equals to square root of this thing times like dx1 wedge dx2 wedge up to dxn. So if you go to new coordinate, just put primes everywhere, right?
Yeah.
And the component of Levi-Civita tensor are given by epsilon mu1 mu2 up to mu n equals to E square root of absolute value of g times E mu1 mu2 up to mu n, and its upper indexed object is written as mu1 mu2 up to mu n equals to this thing by this thing, right?
Yeah.
Okay, so I think these are all right. Still, we need to learn a few more things. particularly we need to know this piercing process that's we haven't seen yet, because we were actually busy defining these kind of things. So piercing process actually concludes the algebra part. Okay, any questions so far? Any questions so far? It's still too long. Okay, I think that's enough. Yeah. You can see the whiteboard, right? Like you can read it.
Yeah, I can.
Okay. Okay. Any questions so far? We just need to learn one more thing. That's piercing process. That's all. Can I continue?
Can we express that generalized chronicle delta in terms of our familiar chronicle
Yes, we
delta?
can. We can. We'll see it. We'll see it.
Okay.
Yes, that's a nice question actually. Okay, so let's complete with this piercing process, huh? Consider you have a grid system. So let's enlarge it. Consider you have a grid system like this. We are talking about 2-dimension. So these like 0, 1, 2, 3. This is 0, 1, 2, 3, like that. Now, if you have two vectors, one is like this, another say this, and you construct a parallelogram out of the whole thing, which would be like this. Question is, what should be the area? So what are the vectors first? Can you write this vector in I'm considering like x hat y hat term, really simpler way. So what is this vector? Say let's call it u and let's call it v. What is u vector?
3, 1.
It's 3x hat
3x
plus that.
plus y hat.
And what is v?
X hat plus y
X
hat.
plus y.
Okay, x hat plus y hat. What's the area?
It is the
cross
cross
product.
product one, just cross product determinant of cross product.
Mhm.
Value of cross product. And
Can you tell me in a simpler way? I just want the result actually, as you have UV defined.
You
Just do
define
the
the
job.
You mean the number? You want the number?
Okay. Let's calculate the area. Okay, so how do I get that?
Cross product.
Okay, cross product. Okay, U cross V, that will give me a vector, but I want an area.
So the
take the absolute value, magnitude.
Take the norm. Take the norm.
Yeah.
This thing. Okay. So how do I take cross product? I forgot actually. So probably you want to write like this: x hat, y hat, z hat, where this bar means determinant, right?
Yeah.
But it's not necessary actually. It's 2D. So can you see it that it's nothing but this thing?
Yes, because z axis will only survive.
So any area you talk, like any area you construct out of vector, it's basically this kind of determinant. It has that kind of determinant in it. So instead of having specific component, if we had like u equals to ux x hat plus uy y hat, and v equals to vx x hat plus vy y hat, the area would be ux uy, determinant of ux uy, vx vy. Do you agree with that?
Yeah.
Okay. Everyone, is it clear to everyone? This is how we can calculate area.
Yes.
So now if we have a vector system in arbitrary coordinates like ux ex plus say two vectors like u vector and v vector. Sorry, uy, that's what I wanted to write. Uy and vx ex plus vy ey. These two vectors I have, some arbitrary coordinate system. So to construct the area, like find the area, I need a procedure that can construct this determinant of this matrix, right?
Yeah.
Okay. So first I have to choose our unit system. So the unit system is the coordinate. So dx would be our unit. So I'm trying to construct everything such that dx wedge dy, this is basically defines the unit grids that we kind of draw over there. Piercing of this thing with u wedge v, that gives me this determinant. So then we'll have like this piercing would have a meaning like something like area. Right?
Yes.
So in previous vector portion, we have already seen that if you pierce alpha with some vector v, alpha is a one form, then this is nothing but contraction of alpha, like takes alpha times v, then contract it. You have already seen it. So we could try for it, right? Let's do the same thing, because contraction is actually well-known thing. It's defined for everything. So take this whole tensor and take contraction with appropriate slot, like 1 to 3. It's right here, 1 to 3 and 2 to 4, like that. So what would be then if you contract like that? What is the contraction procedure? This dx wedge dy times u wedge v, this whole thing has 4 slots, right? 2 of them can take vector, 2 of them can take one form.
Yeah.
I think
What?
you have to write it in opposite way, slots.
Which way did I write?
The upper slot, 2 upper slot, then 2 lower slot.
No. I want to contract this thing to that thing and this slot to that slot, right?
Okay.
No, but the position of the slots, because the first one is one form, so it should take a vector.
So so upper, so the slot will be upper one.
So yes, okay, yes. So you can write like dx wedge dy, that times u wedge v. Now you're feeding these slots. It has total 4 slots. First with a vector e mu, the second with another vector e nu, the third one with a contracting one form, that is omega mu, right? Summed over mu, where you have then omega nu. This is what you're trying to do, right?
Yeah.
Okay, so let's do it explicitly. So expand these wedge products first. If you expand those, you get dx times dy minus dy times dx, right? This is one thing.
Yeah.
Then times u wedge v, you need to perform that. What is u wedge v? It's taking so much long. Okay, so what's u wedge v? Can you tell me?
U
U times v minus v times u.
No. You have to consider this too as well. Otherwise, you cannot do it appropriately. Oh, okay. So yeah, let's not expand it. Yeah, we can do that as well. So for now we can do this u times v minus v times u. We can do that because eventually we're in 4 slots we're substituting something, so it will be eventually fine, right?
Yeah.
Yeah, this is what we're trying to do. So you have to multiply this whole thing. How many terms should you get? 4 terms, right?
Yeah, 4.
So one is dx times dy times u times v, right?
Yeah.
And it'll have 4 slots: e mu. I'm substituting e mu, e nu, omega mu, omega nu, right? This is one term. Then plus, actually it will be a minus term, minus dx times dy times v times u, right? Then another minus term,
Minus dy times dx
dy times dx
times
times
u times v.
then e mu, e nu, omega mu, omega nu, then
Plus
this
dy times dx times v times u.
plus dy times dx times v times u, right?
Yeah.
Okay, so now we are ready to actually perform these things. So when you substitute e mu in the slot of dx, what do you get?
It's a Kronecker delta. Depends on mu. What is mu?
Mu could be anything, so it's a summed over.
So we need to give an index to dx, to dx1.
Yes, so we are calling like x equals to x1 and y equals to y1, like that. X2.
So in that case, it will be Kronecker delta 1 mu.
Kronecker delta. Actually, it's also standard to say like this, like Kronecker delta x. So Kronecker delta can take 2 values, like mu can take 2 values. Mu is either x or y. It can take 2 values.
Okay. X
So
mu.
yes, x mu. Then Kronecker delta
Y mu.
y nu. Then v is getting pierced with omega mu. What is v?
It's v mu. It's the vector.
What is v?
Vx ex.
Vx ex plus vy
Plus,
ey, right?
yeah. Shouldn't it be upper v upper x?
Okay, so it will be yes. Let be a little bit more careful. So yes, let's write it this way. Okay, so then here
So it will,
you cannot actually decide now, right? So you have to
yeah.
write v mu. Sorry, not v. This one is u, right? This one is u. You have to write
u mu.
You have to write u mu. Yes, you cannot decide at this moment because it could take 2 different values. So u mu, then v mu. Yes, then minus
X Kronecker delta x mu.
okay, Kronecker delta x mu, Kronecker
Kronecker
delta
delta y mu.
y nu,
V
This is
mu.
right? Yes, V
U mu.
mu U nu.
Yeah, V mu U nu. Yeah.
Okay, then minus
Then Kronecker delta I mu.
Kronecker delta
Y mu.
Y nu.
Mu.
Yes, then Kronecker delta
X nu.
X nu. Then
U mu V nu.
mu V nu. Okay, then plus
Kronecker delta Y mu.
Kronecker delta Y
Mu.
mu. Sorry, yes. Kronecker delta Y mu. No, it should be opposite. This term should be opposite. Oh, okay. No. Yeah. It's X nu.
Yeah.
So then
V mu U nu.
U nu. So now you can see like we have several terms multiplied. So this term is appearing twice, I believe. Right? This thing is appearing twice.
Yeah.
So the way you can factorize it is so let's factorize U mu V nu, this part. So what do we have in front of it? Kronecker delta X mu, Kronecker delta Y nu minus Kronecker delta Y mu, Kronecker delta X nu, right?
Yeah.
And then plus Kronecker delta Y mu, Kronecker delta X nu. Actually, let's put a minus sign as well. So let's write this one: negative delta X mu delta Y nu plus Y mu delta X nu. V mu U nu, right?
Yeah.
So what's the difference between these two parts? So remember, mu are dummy.
Interchanged.
Mu and nu are dummy indices, right?
Yes.
Yeah.
So we can, instead of writing mu, we can write nu, right? For the second term. And instead of writing nu, we can write mu. I believe I changed it appropriately.
Yeah. Yeah.
Then what do you get? I believe you get twice delta X mu, delta Y nu minus delta Y mu, delta X nu times V mu, U mu V nu. U mu V nu.
U mu V nu. Yeah. Yeah. It's correct.
Okay. Just remember this step. This step is going to be useful. So next we can actually perform these Kronecker deltas, right? So for the first part, so it gives you like ux vy minus, for the second part it gives you uy vx. So is this the area that we are looking for?
This is
Yeah.
twice the area.
It's twice the area. It's not the area. It's twice the area. So basically, this is the thing. So that means, so just the ordinary contraction would be helpful. The ordinary contraction would be helpful as well, but we have to be careful about the factor. So what is your guess what the factor is here? So when you're piercing these two things, so dx wedge dy, because I want this thing to be, this piercing to be my area, we are defining such a way. So what's the relation with the piercing contraction? What's the factor?
1/2. 1/2.
Half. You have to multiply this thing by half. So is this true for every cases? So if you have piercing for n number of objects, say like if you have a piercing of p form between two p forms, if you have piercing between two p forms like alpha and v, so alpha is a p form and v is a p vector. So you can assume that should be proportional to, like equal to some factor times contraction of these two things, complete contraction, right? So what should be the factor? What do you expect? Like as you can see, for two form we had half.
I think 1/p factorial.
It should be 1/p factorial, exactly. So that's how we defined our piercing for p arbitrary p vector and p form. Such a way that it gives you proper volume or proper area. You can try it for three dimension as well. So finally we are on the position to actually give you something. So here we want, like for the basis p form and basis p vector, if you have a piercing between those two, then you have everything. So for say basis p form is like omega mu1 wedge omega mu2 wedge up to wedge omega mu p. So this is basic p form, right? Basis p form. So piercing with that a basis p vector, that is e nu1 wedge e nu2 wedge up to e nu p. What do you expect actually? Okay, let me help you. If mu1 equals to 1, mu2 equals to 2, and so on, like mu p equals to p, and also nu1 equals to 1, nu2 equals to 2, and so on, like up to nu p equals to p, then what do you expect?
Relation with contraction.
So when you have a unit volume element and unit p vector, right? Like as I said, like nu1 equals to 1, nu2 equals to 2. It's basically giving you the unit basis. So what do
I
you expect?
1.
Yes, we expect 1 in that particular case. And now observe another thing. If you switch mu, any two indices between mu, then you get a minus sign. Also same thing is true for nu. So which object do you have which has a value either +1 or -1 depending two set of indices?
Kronecker delta.
Kronecker delta. So you could say this is our definition of piercing, is we have defined like this. This is the definition, and this definition agrees with the other definition as well.
Okay, how much time you will take more?
No, I'm done actually. So this is the piercing. We have already defined it. So I'm just adding the last part over the tabulation I started. I'm done. Oops, it just crashed.